Y'all got any questions on the lab? Are we okay? Decoders and encoders, right? So what does decoder do? Yeah, decoder.
Break down the actual circuit in order to put out a true logic.
We could say that about any digital logic. I don't. So a decoder takes a binary number and converts it into another base or another code, right? Okay. Or a binary code. Basically, a binary code we're looking at is either binary or BCD. And then an encoder takes a code or another number system and converts it back to binary.
Okay, so decode goes from BCD to binary.
Well, decoders goes from binary or a binary code, and the only binary code we're looking at is BCD, into another numbering system. So we have a 7442, which is a BCD to decimal decoder. And then we have a 74138, which is a octal, is a binary to octal decoder. So it's only got 8 outputs. The 7442 has 10 outputs. And then we have a 74154, which is a hexadecimal, which is a binary to hexadecimal decoder. So it's got 16 outputs, right?
Yeah, 45, 42.
What's that?
We had one like 45.
We had one for the 7442, and I think that was the only decoder we had. But there's other ones out there. So ours was a BCD to decimal decoder. So we brought in the BCD code, and then it outputted a single digit output depending on what number I brought in. So if I brought in a 7, a BCD 7, output 7 went low. It has low active output. Now the 74138 is a binary to octal decoder, so it's going to have 8 outputs, 0 through 7. But what they add with the 74138 is they add the enable pin. So the 7442 does not have enable pins. And what do we mean enable? We mean we allow the outputs to respond, to do what they're going to do, right? We're just looking at it. We asked if y'all got questions about it. That's what. So no, we're not going to really go over it, but I'll bring it up if y'all got questions. Y'all see 7442? 74, 74, 192. What do you see 7442 at?
Talking about on the printer?
No, I'm looking for the data sheet.
I tried to pull it up last night on my computer, but for some reason it won't let me open up PDF. I did it last week too, but I tried to wait it out.
Oh, here it is, 7440. No, we did the pinouts in the lab though, right? I mean, when I did the lab. So this is a 7442. Let me turn on. Well, there's no such thing as a BCD, a 4-bit BCD 11, right? You understand? So what it does, here's the truth table. So the truth table, that's the actual makeup of it. So think about all the transistors here that would be required to do this. But technically, guys, you don't even need to know this, see? All you need to know is what it does, right? You understand? So we find the function table or truth table, and here it is. So if this right here, this would be a BCD 0, which output goes low. 0. This would be a BCD 1, which output goes 1. This would be a BCD 6, which output, this would be a BCD 9, so which output went low. Now, if I put anything above a 9, all the outputs go high because it can't decode that, right? Y'all understand that? So it's not going to blow up. It says invalid. It just means there's no output that would represent those combinations because they're not true BCD, right? You understand that? I need to put all these in one same place. Looking for a 138. Okay. So the 138 is a decoder, right? Demultiplexer, and we'll see that again today. But this guy here, here's the 138, here's the 139, which is the one that we're dealing with. So they're covering two with the same data sheets. This guy here's only got 3 inputs, A, B, C. So how many combinations can we put on this? We can only put 8, right? 0 through 7. And here's the outputs. 0, 1, 2, 3, 4, 5, 6, and 7. And they're low active outputs, kind of like the 7442. This has 3 enables on it. So enable 3 has to be low, enable 2 has to be low, and enable 1, they're calling this A and B, and then label 1's got to be high. So it says, okay, if my enables are, if the G2, so it's using them together, is high, then all the outputs go high, right? You'll see that. If G1 is low, then this guy right here don't care, all the outputs are high. When this one's high and these two are low, then if I put all lows on the inputs, then output 0 goes low. 3, 4, 5, 6, and 7. Here's a 74154. We're going to use it today as a demultiplexer. So we can use this as a demultiplexer. But this is a 4 to 16 line. So look at this thing right here. This is what makes it up. But we really do, I'm not multiplying. This is a 4 to 16 decoder. I really don't need to know what's inside that thing, right? You understand? Because if it don't do what it's supposed to do, then odds are it's bad. But I need to know what it's supposed to do. Y'all understand that? So this guy's got 2 enables right here. So if these two, before this guy out here works, before it decodes, then both these have to be low. And here's the pin out. Here's G1, G2, they're low active. And then how many outputs does it have? Well, it's got 0 through 15, because it's a 4 to 16 or a binary to hexadecimal decoder. So this says if G1 and G2 are low and all the inputs are low, then 0 output goes low. We can go all the way up to 16, which would be here, which would be, 15. They're all low. Output 15 goes low. If the G1 is high, then everything is what? Don't care, yeah. If these two are high, then it don't care, and all the outputs go high. So these are decoders, right? Make sense? Now the encoder that we looked at was a 74147. So what we're going to do here is we're going to bring another numbering system. This is 0 through 9, so this would be a decimal to binary decoder, right? You understand that? Encoder. And then what we're doing, we're combining this with a 7447, which is a BCD or binary to 7 segment decoder. This would be definitely another code, right? Understand? And so we looked at 7-segment displays a little bit, right? You understand that? This is a common anode display. So what does that mean? Give it your best shot, Brian. At least you might not get it right, but at least you're not sitting there like a knot on the log, right? I appreciate that. I really do.
It means that it allows on certain not binary.
Well, a 7-segment display, and y'all see these all the time. It's just that you know they're still all out there, and they still use LEDs. Most of the time, they use LEDs at baseball games now. Basketball up at the top, yeah. And you can see a 7-segment display just has these things that we refer to as segments. So you can count the segments. We call this is named the A segment. This is named the B segment. This is C. This is D. This is E. This is F, and this is G. Now, what can we do with this thing? We can show numbers and some letters, right? So I could, if I can control it. But now we're going to come up here, and this is what we call a common. This is what we call a common anode. So all these things are is LEDs. You forward bias them, they turn on. You reverse bias them, they turn off. So this is still the anode. So we're going to make this positive in respect to this wire right here, which we call the cathode. We've already talked about this, right? So an LED only lets current flow in one direction. Now, the true symbol of an LED is this, and it's supposed to have arrows coming out of it. But these are 7-segment light emitting diodes, and they don't have time for the arrows, so most of the time you look at this, they're not going to draw the arrows. And I've probably got 8 of them in there. Now, the 8th one is usually a decimal point, like a right-hand decimal point or left-hand decimal point. So you wouldn't see that at a ball game, but, you know, if we're going to have a calculator, calculators usually has decimal points, right? And what we mean by common anode is they just come up here and connect all the anodes together. And of course, what we're going to do with this guy is we're going to come up here and connect this up to plus 5 volts or through a resistor like in the lab. The problem with in resistor, using a single resistor for all 8 LEDs is the more you turn them on, the dimmer they get, right? Understand? So the preferred method is to come over here and put 1 resistor per lead. Rule of thumb, you would have to look this up, is rule of thumb, the LEDs drop around 2 volts. Just to make them work. Anything above 2 volts is a short circuit. So if I was to come over here and connect this to ground, that's 3 volts worth of short circuits. Short circuits means maximum current flow, and you burn your LED up just like that. So we have to have that resistor in there to limit that current and drop the rest of the voltage. So that means I'd come over here, if this guy's dropping 2 volts, and I'd choose a resistor that would drop 3, right? You understand? At whatever current I wanted the LED to work at. And you would look at that. And of course, we're using 330 ohm resistors, and they're dropping 3 volts. So how much current are we using to run these things? I is equal to V over R, right? So y'all tell me, get out your calculator and calculate that. It's going to be in the milliamps. Usually around 16, 17 milliamps is what we want to run through these things. 15, 10, you see 10 used a lot. This looks like it's going to work out to be a 10, don't it? Because I got 3 of them.
That equation looks like it's a 110. Oh, that's
I don't know what you're. 9 milliamps. Okay. Not extremely bright. 330. Sometimes they use 470s to make them last a lot longer. So, and then they would have names, right? You know, usually when we draw it, we just start on the left and move toward the right. So this might be the A segment, this might be the B segment, C, D, E, F, G, and this right here would be the decimal point. I think ours has a right hand or left hand decimal. But it's what we call, and if you buy these, this is going to be CA for what? Common, yeah, common anode. And then of course you'll have a color, right? We can get a pretty good deal of colors with these. And then of course it would come up in then it would come up here and put like RDP. That would mean right hand decimal point, right? And this is the way you'd buy these things. So what do I need to turn these on? Well, I need to turn these on with a low. That's the ripple blanking stuff.
Okay.
So we're not looking at that right now. Okay. So normally, I don't know if you've ever taken videos and went around and looked at your cable box. But a lot of times you'll see those things blinking and it looks like they're standing because your camera's taking pictures, but they're not in sync with those multiplexed inputs. So what they like to do is like these lights right here, these fluorescent lights are blinking at us 120 times a second. But our eyes see them what? On all the time. This monitor up here is blinking at some refresh rate, usually 60 times a second. But to us, it looks like it's in motion, right? Remember when they first had the movies, they were just individual pictures and people would look through a thing and they'd turn a handle and it would flop up, and they thought that was so cool because it looked like they were actually true movies, but it was just somebody taking a lot of pictures, right? In fact, we had a guy when we was over in Japan, he bought a camera where he could shoot still frames with it. It was a movie camera, but he could shoot still frames with it. And we'd get on the floor and we'd slide all around on our butts and everything, and he'd take single pictures, and we'd have a steering wheel and it looked like we was doing what? Then you'd play the movie and it looked like we was what? Driving. You see that every once in a while on commercials and stuff like that where people are sitting down and it looks like they're in motion, you know. But so what we can do to save hardware and plus lines is we can multiplex these things. So we can come over here and use a common data line, and then we can have multiple displays up here. And then I could turn on this one, I could turn this one on, and this guy right here would be what? Off. Then whatever I wanted this guy right here to display, I would put it on these data lines right here. And then I would turn this guy here what? Off, and turn this guy right here on, and then what I wanted that display to do, we would turn it on, and then we'd put its data on the data line using multiplex. So what I've done, instead of having 4 data lines for every display, we're using the same 4 data lines for all display, but we're multiplexing them, right? Because we're blanking. Blanking means to turn off. Like this display on my computer blanks when it goes left. So images on computers are made from left to right, and they do it one line at a time, believe it or not. One line at a time from left to right. But what happens when it comes back from right to left? Well, they turn it off, but we can't see it because it's done what? Yeah, it's done so fast we can't do that. But every once in a while, if you're taking movies inside your house and you go by your cable box that's got the channel number, you'll see them suckers look like they're flashing because the refresh rate on your camera is doing this is not synchronized with the refresh rate on your display. But what it does, it saves data line and it saves integrated circuits, right? You understand that? So anytime we get into a situation where we can do this, they're going to do this. This monitor up here, this function generator uses a multiplex display. So what it's doing is it's turning off one and allowing the next one beside it to work. And that's what your ripple blanking and your lamp. Of course, lamp test means you just turn on all the LEDs, right? So 7447 is an open collector. What does that mean? Because we don't need to provide the high. The highs are already there. So all this guy does is provide the low, or provide the ground. So that's the output of the 7447 right there. It turns that transistor on, the LED turns on, turns the transistor off, the LED goes off because there's no current path, right? You understand? Yeah, so that's what the 7447 does. I put a binary code into it for a 3, and it automatically decodes that and brings the segments low that'll display a what? A 3. I put a 4 in there, I put a binary 4 in there, and it automatically, it decodes that and turns on the segments that will display a what? 4, right? You understand that? So I could take this guy right here apart, and I guarantee there's at least one 7447 inside that thing, at least. We might do that, so maybe I won't be a liar. So what we're doing is we're taking a encoder that I can bring a decimal number into it from 0 to 9, and it's going to decode that, send it to a 7447, and the 7447 is going to display the number. And that's the last one that we already talked about that. So this is the 74147. So this is a what? An encoder, right? So that means if I come in and I still have this one hooked up, guys, it's very impressive. I know what you're talking about. I know what you're talking about, Mike. Yeah, I started showing symbols, right, to represent. That was a 7440. That was a 7447. So you can put numbers above. You can put numbers above 9 on there, but basically that's the highest digit, right? That's the highest decimal digit. You know. Kelvin, look up, man. Or just actually. What was that? One of the. What was that? One of the yeah, he had his eyes painted on his. Had his eyes painted. That was it's one of the Pirates of the Caribbean movies where Jack Black was had his eyes painted on this thing. But I've seen it on several movies. Okay, y'all help me find it again. 7447. Here we go. It's not be the same. So lamp test, this is that if we bring this low, it turns on an A, right? Does that make sense? These are your ripple blanking inputs. So we use these guys right here to blank it so I can multiplex them, right? This doesn't show the characters. This must not be the same one that's on the. So if we put a 0 on it, it decodes a 0, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And then if you put a 10 on it, you get this little thing like this. If you put 11 on it, 11 on it, you get this, 12 this, and you put a 15, it blanks it. And that's the actual makeup of the 7447. Do I need to know that? No. All we need to understand is what it does. So think about wiring just that one IC up, that 7-segment decoder. Just think about wiring that up with nothing but transistors. I mean, we're talking about a lot, right? These have open collector outputs. What does that mean? It means there's no sourcing transistor. It cannot output a high, but it don't need to output a high because the high is already there, right? You understand that? Now, 7448 is a common cathode driver, but it basically does the same thing. 7447 is by far the most popular used, and it's a common anode driver.